All right, what up, fam? We're going to start off with the confidence intervals, like going over it. I will be going into the test review soon, so if you want to just hop right into the test review, skip ahead to where that starts. But I'm going to go ahead and get going through confidence intervals in general, just in case someone needs it. I heard someone say in class that they said, I have no idea what's going on in this class right now. So I figured I should just go over it completely. Anybody who wants to hear it. So, what is a confidence interval? Here's my definition. This is the Mr. Richards definition. That's why I put it in quotes. It's not a book definition, but mine. A range of values that could reasonably contain the true value of a parameter of interest. Now, what is a parameter of interest? Parameter of interest could be literally anything. The example I've just made up here is the percent of times fallen asleep in the last week, and I made these numbers up of 0.14 to 0.71. And what that would mean is it is reasonable to believe that I fell asleep on time between 14% and 71% of the days last week. So that's all that means. It's values that are reasonable to believe. For all the math questions, it is always going to be a formula that is the point estimate plus or minus the critical value, which is also known as the number of standard deviations, multiplied by the standard error, which is really a standard deviation divided by the square root of n. And here are two fancy versions of the formula, where p hat is a version of a point estimate, z star is a type of critical value. This right here is a type of standard error. This is our x bars, our mean. T star is the critical value we use for means, and this bad boy over here is our standard deviation divided by the square root of n. Anytime you do a confidence interval, there's going to be a center. So like on this one here, the center of this one's our point estimate would have been proportion, and then it would have went left or right a certain number of standard deviations. Over here, the logic here, you can only actually run these things if there are certain conditions that are met. You have to check three things for all confidence intervals. Either going to be random, that is to say it's a simple random sample, has to be stated in the question somewhere. There must be the 10% or the independence check, less than 10% of the population is sampled. In the problem, we're going to see examples of this later. And for the normality, there are two different versions of it. P hat has what's called the large counts condition, where you're checking do n times p and n times 1 minus p, are they in fact greater than or equal to 10? Or if you are in an x bar situation, a mean situation, the distribution was normal, or n was greater than 30, or the dot plot, or similar, a box plot or histogram or whatever, shows no outliers or skewness, or the normal probability plot is a straight line. So you got to pick one of those. Literally doesn't matter which one. If the distribution was normal, that's the easiest. N greater than 30, second easiest. Dot plot and NPP, probably similar in easiness. Just those are the ones you do last, only if you have to. All right, so that was my quick little rundown. Hopefully that was good enough. If it wasn't, life goes on. We're going to see some more examples here. Let's actually do it. Here we go. Your teacher claims to produce random numbers from 1 to 5 inclusive. That just means it includes 1 and 5. But you've been keeping track. In the past 80 rolls, the number 5 has only come up 8 times. You suspect the calculator is producing fewer 5s than it should. You would like to construct a 95% confidence interval for the true proportion of 5s generated by this calculator. Which of the following options gives the correct notation for the point value of the for and value? Oh, I understand. Correct notation for and the value of the point estimate. There you go. I can read. So first of all, all the ones that are estimates are the ones we could possibly have. So we're gonna go ahead and cross off this letter P here, because those are for proportions. The actual true value. Remember that you're gonna be using a point estimate, which is always a P hat or an X bar. We can immediately cross off this P hat being 8, because that is total nonsense. You can only have proportions between 0 and 1. We knew that from way earlier in the year. And for the P hat here in the X bar, which one is it? Well, anytimes you're trying to figure out a yes or no, is it showing up or not showing up, that is a proportion. And that's what we're doing here is letter B. This would be for a mean if you're like asking the number of times that a 5 showed up, and you're creating a confidence interval, not for proportions, because it does say proportion in the question, and you actually wanted the number of them, then you would do X bar. All right, let's do number 2. A researcher studying reaction time of drivers states that 95% confidence interval for the mean time it takes for a driver to apply the brakes after seeing the brake lights on a vehicle in front of him is 1.2 to 1.8 seconds. What are the values of the point estimate and margin of error for this interval? So in this one here, we have a 1.2 to 1.8. So those are the edges that we were talking about before. So I'm just going to write it like that instead, because that's kind of how we're going to be used to seeing it. In order to find the point estimate, the easiest way is to add these up and divide by 2. 1.2 plus 1.8 is 3, and you're dividing by 2, and you'll get 1.5. So there's our beautiful little point estimates. And because 1.5 is in the center, it goes all the way to 1.8, and it goes all the way down to 1.2, and therefore our margin of error is how far apart those are, which is going to be 0.3, which you can calculate by doing 1.8 minus 1.5 if you needed to write that. 1.8 minus 1.5 is how you get that 0.3, or you could do 1.5 minus 1.2. Regardless, our margin of error is clearly 0.3, so our correct answer is letter B. Easy enough. 2 letter B's in a row. Let's do number 3. A 95% confidence interval P for the true proportion of all shoppers at a large grocery store who purchase cookies was found to be between these two numbers. Which of the following claims is justified? The majority of shoppers purchase cookies. In fact, the opposite. Fewer than the majority, because all of the confidence intervals below 50%, so definitely not that. At least 28%. Actually, no, not at least 28%, fewer than 28.2%. At least 23.6% of shoppers purchase cookies. That is reasonable to believe. It is completely reasonable to believe that it's above it, so that's a reasonable answer, but let's double check the rest of them here. Less than 25% of shoppers purchase cookies. That's not reasonable to believe, because it's reasonable to say that it's between 26, 27, 28% could all be possible, and 95%, well, obviously not even close. So letter C is our correct answer. Let's move on. Number 4. An agricultural researcher plants 25 plots with a new variety of corn. A 90% confidence interval for the average yield for these plots is found to be this 162.72 plus 4.47 bushels per acre, which of the following produce a confidence interval with a smaller margin of error than this one. So the big, huge idea here is the margin of error is the portion of our formula that is on the outside out here, the critical value times the standard error. So it's going to be one of these two. Because Z star and T star are set in stone, they are going to be determined by the confidence percentage, the confidence level, the 98%, 95%, whatever it is that you're trying to get, the number of standard deviations. So you're really looking at this part of the formula here when you're looking at this margin of error, which means you got to be thinking about the fact that it's always going to be, I'm going to use the proportion one just for, actually, I'll use the other one. Let's use the T star one, because that's what this is. Our margin of error is going to be T star times our standard deviation divided by the square root of n. And we're trying to figure out how can we make this small margin of error smaller. So we can decrease T star, but that's not really possible because 90% sets T star in advance. If we changed the standard deviation, that'd be like faking the data, so that doesn't make sense. But the square root of n, you can change the sample size pretty easily. To change the sample size, if you made the sample bigger, if n goes up, then this entire thing will go down. So the margin of error will go down if n goes up, because you're dividing by a bigger number. And likewise, if n goes down, the margin of error is going to go up. So the bigger your sample, the lower your margin of error. So we just need to figure out which one of these says that. Using a 95%, that is not true, because a higher confidence will actually increase, because our higher confidence here is going to make that a bigger number, so that's not going to be good. Reducing bias, that's just nonsense. You can't have, if you have a bias study design, you can't really do confidence intervals anyways, because you'd be rejecting that random portion. Planning 100 plots, that's the answer right there. That's what we're looking for. We're looking for the increasing n. 25, no. None of the above. Nonsense. Yeah, number 4 is definitely correct. So we've had 2 B's and then 2 C's. Let's do our next page here. So, oops, it's a front and back type of situation. All right, number 5 here. A 95% confidence interval for the mean reading achievement score for a population of 3rd grade students is 44.2 to 54.2. Suppose you construct this 99% confidence interval using the same data. Which of the following statements is correct? So now we have increased our confidence level. Because we've increased our confidence level, that is also going to increase the width of our confidence interval, because we are increasing the Z star, we're increasing the T star In this case, it's a T star because it's a mean reading achievement score. So which one is true? It's going to have a wider situation, letter C. Number 6. A radio talk show host with a large audience is interested in the true proportion of adults in his listening area that still read printed newspapers regularly. To find out, he poses the following question to his listeners: do you read a printed newspaper more than 3 days per week? He asks listeners to phone in and respond yes or no. Of the 100 people who phoned in, 30 answered yes. Which of the following assumptions for inference about a proportion using a confidence interval has been violated? Right here. Random sample. Very particularly if you're trying to be smart and being prepared for this AP test later, remember the correct word for this. This is a voluntary response bias. I'm going to write that down. Voluntary response bias. Because it does say he poses the question to his listeners, and it's of the 100 who phoned in, so it's just whoever decided to call him up. This is not data you can do for a confidence interval. Ain't gonna work for us. Let's go to number 7. A random sample of 900 individuals has been selected from a large population. It was found that 180 of regular users of vitamins. Thus, the proportion of regular user of vitamins as the population is estimated to be 0.2. What is the approximate value of the standard error of this estimate? So our standard error, we already pointed to it earlier today when it comes to proportion. It's that same exact formula. So I'm going to be writing it down one more time. We got a p hat. We got a 1 minus a p hat. We're dividing by n. In this exact situation, we're going to be doing 180 over 900, which happens to be 0.2. It already tells us that. So they told us that p hat is 180 divided by 900 is equal to 0.2. So this is going to be 0.2, big, huge square root. This thing, 1 minus 0.2 is going to be 0.8. And dividing by n, it was 900. So we have to throw all that stuff into a calculator. And I did this earlier myself, so I know that that answer happens to be letter D. Let's do question number 8. So question number 8, a newspaper conducted a statewide survey concerning the race for state senator. The newspaper selected a random sample of 1,200 registered voters and found that 620 of them planned to vote for the Republican candidate. Let P equal the true proportion of all registered voters in the state that plan to vote for the Republican candidate. Which of the following gives a correct 90% confidence interval for P? So this one, if you notice, all these guys have the same exact P hat, the 0.517. So that's going to be 620 divided by 1,200. And that is going to be the 0.517. So that's like this is like where our center is. That's our point estimate, we're going to be calling it. And now we're going to need to figure out the 90% confidence interval. So whenever you're doing 90% confidence interval, there's going to be 2 approaches. You can either use the formula or you can use the calculator. Because the calculator is going to be so much easier to use, I'm going to go ahead and say, let's start with the calculator for these multiple choice portions. So what we're doing on these, this is called, because you have a single sample, this is called a one sample Z interval for population proportion. Sorry, I wrote that small and unlegible, illegible. One sample Z interval for population proportion. I apologize for the handwriting one more time. It's not going to get fixed. All right. So to actually do that on our calculators, what we're going to be doing is we're going to be hitting the stat button. We're going to scroll to the right where it says tests. And then we're going to be scrolling to the letter A. That's where you find this one sample Z. So let's go ahead and do that really quick so we can see what that screen looks like. So again, we're going to be hitting that stat button right here, scrolling over to the word tests. And then you need to be scrolling down, really. I should have written like down maybe on the arrow. And you're going to be scrolling down to the letter A where it says the one proportion Z interval. So there's our one sample proportion Z interval. So you hit enter on it. It looks like I have some stuff from earlier. The X value is that number of successes. So on this particular question, it was 620. For the next one, the N is the sample size, which I believe was 1,200. Yep, 1,200. And the confidence level, we were told, was 90%. We do need to write our C level as 0.90. We got to use the decimal version. So we're going to go ahead and 620, and then we're going to write 1,200. And then we're going to go ahead and write our 0.90. It deletes the 0 for us, and we get this number. So how are we going to figure out this? Well, the deal is that is our edge of our confidence interval. So we know like the interval is from 0.49294 to 0.54039. So if I simply did this number minus this number, so let's go ahead and do that really quick. We're going to subtract the edges. We're going to find the dead center because that's the dead center of it. So if I just did 0.54039 minus 0.517, I will get my final correct answer. So 0.54039 minus 0.517. You got this, and you're going to get 0.02339, which happens to be letter C here, 0.0024. So I do think that's the easiest way to do it. You just plug all the numbers in the calculator, and you're done. However, you're still going to have to use the calculator if you want to do it the long way. So the long way of doing it, so you want to skip the number 9, you want to fast forward a little bit if you're just going to do it this way. But if you're not going to do it this way, the longer way is to either use a table to get the Z star or to use the calculator to get the Z star and then multiply it by the population proportion. So I'm going to kind of write it up here, and I'm going to write it in red to make it very, very clear. This is part of the other problem here. But if you wanted to do it on your own to figure out what this margin of error, this number over here on the right is, we're going to be having to do our Z star multiplied by the square root of our p hat times 1 minus p hat, all divided by n. So we're going to need to figure out that Z star. To figure out Z star in the calculator, so Z star in the calculator, we're going to be hitting the inverse norm button. So this is Z... You can read that over there. Barely. I'm going to slide this paper. Z star in calc. We're going to be hitting the inverse norm button, which is going to be vars, second vars. And after you hit second vars, you're going to be hitting the inverse norm. And after you hit the inverse norm, you're going to have to answer a question about area and confidence. So our area is the only thing I really care about here, because I think you can figure out the rest. And that's going to be 1 minus that confidence percent divided by 2. So let's go see that really quick. So if you go in here, we're going to hit second first, and then we're going to hit vars, and then we're going to inverse norm, number 3. And the area is 1 minus the confidence percentage divided by 2. And I misread parentheses there. So parentheses 1 minus, and again, in decimal format, I believe it was 90%. Yep. 0.90, and then divide by 2. We're going to go ahead and paste it. And we get this negative 1.6448. Now, on the actual table, it says 1.645. Doesn't actually really matter there because that's a rounded value. This is like the better value in a lot of ways. So we're going to go ahead, and we don't need the negative sign there because it's plus or minus in the question. So we can ignore the negative sign, 1.64485. I'll leave it as a 9, I suppose, for 4 decimal places. And then we have to multiply this by our p hat 1 minus p hat over n. So we have to do, we figured out it was 0.517 here. So it's going to be a big, huge square root, 0.517 multiplied by 0.4, I can't do math, 483 divided by 1200. And if you throw all that into the calculator, you're still going to get this number down here. So let's check it out. So first, I'm just going to do a little bit of light cheating. I'm going to take this guy times the square roots, and we're going to go ahead and... Does this have the updated button? No, it doesn't. The newer calculators, you can just hit this button instead of doing alpha y equals enter for your fraction. Anyways, we're going to go 0.517 times 0.483 divided by 1200, and we can see that it is 0.0237, which still rounds to 0.024, but in fact, we got a better answer, 0.023, 0.02339. So you can see it's actually a little bit different, at that last decimal point. So this is actually like the better answer in a lot of ways, this one right here. But I'm done talking. I gave you the 2 different ways. Regardless of what you do, you get the same answer. We're moving on with our lives to number 9. All right. So, a newspaper conducted a nationwide survey concerning the 2008 race for state senator. The newspaper selected a random sample of 1,200 voters. The same exact one looks like. Which of these following is closest to the sample size you would need in order to estimate P with a 0.01 error? So, this is going to be, in my opinion, one of the hardest questions on the test because of the algebra that you have to do. You have to like kind of memorize the algebra, or you have to memorize the formula that gets to the algebra. And I don't know. For many students, the algebra will end up being easier, or just taking the L on this particular problem, moving on with your life. That's totally acceptable too if algebra is just not your thing. But here's how you actually do it. So the margin of error is going to be the Z star process. So our margin of error here, we want it to be less than or equal, because you're trying to make it less than or equal to. So our margin of error is going to be less than or equal to our Z star multiplied by our square root of p hat times 1 minus p hat divided by our n. That is our margin of error, and less than or equal to this thing, because we're trying to make it less than 0.01. So we have 0.01 less than or equal to Z star. Exactly the same method I was previously describing up above. And this time we need to get 95% confidence. If you go ahead and do it, we hit second vars inverse normal 1 minus 95%, and we're going to get this number 1.9599 that clearly rounds to 1.96, and that is a number I kind of actually recommend people to memorize because it shows up so often for our Z star situations. That 1.96 number, let's use it, 1.96 multiplied by, and now we have to do our big huge square root. It did say in the question to use p hat as 0.5 as approximation of p, so 0.5 times 0.5 divided, because it's 1 minus 0.5, divided by n. And that's what you're trying to figure out, is this guy. Now, at this point in time, we have to figure out which one it is. You could, if you are not the best with this stuff, you could actually just plug in all these numbers and figure out which one gets you closest to 0.01. Actually doing the math, though, I'm going to go ahead and go through the algebra. I'm going to run, I think I'll have enough room. So we're going to go ahead and divide both sides by 1.96. I'm also going to go ahead after that. So I'm dividing both sides by 1.96. I'd have to copy the square root normally, but if I square both sides, I no longer have to look at that square root symbol. So I'm going to go ahead and square both sides so I don't have to look at it. Also, it's 0.5 times 0.5, which is 0.5 squared. Now we're going to flip over both sides of the inequality. And when you do that, the direction of the sign switches. It's an algebra rule many students end up forgetting. And then it's going to be n, and it's going to be divided by this 0.5 squared, right? But if it's going to be divided by the 0.5 squared, the 0.5 squared is going to be on the other side. And this number has to be greater than or equal to n. So if you notice, we're going to round up no matter what on this one. So because you can't make the sample size smaller. So whatever number we get here, we're going to round up, even if it's like, I don't know, 4,799.1. We're going to round up that 0.1. We always round up for these questions because of that greater than or equal to. If we throw all these numbers into the calculator, 0.5 to the power of 2 multiplied by 1.96 divided by 0.01, and we got to square that bad boy as well. And you do all, you get 9,604 exactly, which is our letter E. Please note, like I said earlier, you could just memorize the formula. I don't recommend it, but just like kind of working backwards, this 0.5 squared was part of our p hat formula. So if you wanted an n situation, I'm going to start by writing n, and we know that n has to be less than or equal to, because the margin of error is greater than or equal to, less than or equal to, and it's every single time it's going to be our p hat multiplied by 1 minus p hat. And both of those are going to get squared in the end, because if you, or sorry, they're not going to be squared, just multiplied together. I don't know why I just said squared. The part that's going to be squared is your Z star and your margin of error. So if you notice the top, the Z star there is going to be a Z star, and that's going to be squared. And then you're dividing it by the margin of error that you're looking for, divided by the margin of error that you're looking for squared. So if you felt like it, you could memorize this. You could also memorize the equivalent one for the T star situation, which uses the Z star formula, which is kind of the worst. But you know, what are you going to do? But in that one, you do actually end up having to square the standard deviation. So that one's going to be standard deviation, all squared, and you're still going to be multiplied by our z star, and we are going to be dividing by our margin of error squared still. I don't think these are worth memorizing, but you could memorize them, but they will, unlike all the other formulas that we've had here, they will not be on the AP test. They're not be giving to you, so you kind of just should just do the algebra. But if you really, really don't want to, have fun memorizing formulas. All right, I'm moving on here. We're doing question number 10. Good news, we actually get to skip number 11 because it's the same exact problem as before because I messed up when I made my test earlier. Whoops, Mr. Richards, check your work before you send it to the printer. All right, number 10, a 95% confidence interval for the mean mu of population is computed from a random sample and found to be 9 plus or minus 3. There's a 95 probability. No, this is one thing I did not cover in my big spiel at the start, but you have a very specific way of talking about this. You only mention confidence, never mention chance or probability or anything like that. It is reasonable to believe it's between two values. 95% of values, no. If we took random samples from each and computed a 95% confidence interval for mu, approximately 95, that is perfect. That is our definition that we are looking for. This right here is called the definition of a confidence level. That's what that 95% is saying. It's saying if I made up if I kept on taking random samples and I took those samples over and over and over again, I found 100 of them, did 100 here, 100 here, 100 here, and I made confidence intervals over and over and over. 95% of all the confidence intervals that I create will capture the true population proportion. We have no idea which 95% of those they are until we've made every single one of them. And then if you've made every single one of them, then you also know what the actual population mean is. So whatever, you'll never do it. That's the answer we want. Let's move on. We're skipping number 11. Like I said, we've already done that question. All right, number 12. The weights of 9 men have a mean of 175 pounds. Standard deviation S. What is a standard error? So standard error is just standard deviation divided by square root of the sample size. So we're doing Sx over our square root of n. So in this one, we got 15 divided by the square root of 9, which is 15 over 3, which is 5. Excuse me. That was easy. Moving on to number 13. You are thinking of using a T procedure to estimate the population of 95% confidence level. You suspect the distribution of the population is not normal and may be moderately skewed. So the only way, we talked about at the very, very start, our checks over here. Our checks over here were saying the distribution was normal. They said it's not normal. Or the dot plot, no outliers or skewness. It is skewed. So the only thing it could be is if n is greater than or equal to 30. Or I guess the normal probability plot, straight line, but that would be causing part of the skewness anyways. Your sample size has to be at least 30. Letter B. Let's move on to the actual lie do, number 14. Whoops. My bad. Below are dot plots from 5 different samples. Which sample does not satisfy the large sample normal condition for performing one sample T procedures? So A and B, looking at them, they're over 30, so they're done right away. So A and B are not the correct answer. All the other ones, though, less than 30, so we got to look at them. So it's not A and it's not B. We are looking for skewness or outliers. I guess we're done. It's letter C, right? Because there's nothing to think about. It's got a crazy outlier. The outlier's all the way over here in no man's land. And yeah, this is clearly not good. This one's like smidgen bit skewed. It has one extra dot over here, but it's not bad. This one has no skewness at all. It's just spread out all over the place. We would call this one, I don't know, flat, somewhat uniform. Actually, is it perfectly uniform? Like on both sides, like one of the dots here in the center? No, not quite. It's close to it. Anyways, number 15. Let's do it in a random. By the way, when I did this one in class, I ran out of room, so I am going to be answering this one on a separate sheet of paper. You may or may not need to be doing the same exact thing. Here we go. So in a random sample of 150 students on a large university campus of several thousand students, 90 students admit to not getting enough physical activity, 3 or more days of vigorous exercise for at least 20 minutes, or 5 or more days of exercise for at least 30 minutes a week. We didn't need any of that information. So, like, this is all useless stuff. 150 students, 90 students admit to not getting enough activities. This is our N. This over here is our success number. So this is going to be telling us that P hat is going to be 90 over 150. And that's pretty much all we need to construct and interpret a 95% confidence interval for the true proportion of all students at the university who do not get enough physical activity. So let's go ahead and do it. So because that's what we are doing, I'm going to go ahead and scroll up here. And we're going to start off with this letter A. So for this letter A, to construct and interpret, the very first thing you have to do is the checks. So our checks are going to be exactly the same. We're going to be answering this AP style. You are allowed to be using a bullet point format for these checks, and that is exactly what I recommend. If you'd rather write it out in a paragraph because you're feeling like an English major, then knock yourself out. I'm doing bullet points. Random. And in the question, literally the first words in a random sample. So you can just say random sample was stated in the question. Boom. Continuing on. After you check random, you want to check your independence condition, the 10% condition. So let's just write it as the 10% condition. The 10% condition is, you could say 150 multiplied by 10 equal 1500, and say something to the effect of, it's reasonable to believe that more than 1500 students are on a large university campus. So it is reasonable to believe that there are more than 1,500 students on a large campus. Okay. University campus, if you want to be more specific. The AP test isn't going to care. All right. The very last one, our normality. The normality check on this one is very, very straightforward because we're in a proportion situation. We are checking n times p hat. We need to figure out what that is. And we also need to figure out n times 1 minus p hat and figure out what that is. For both of these, it's going to be very, very straightforward. Our n for both of them is 150. We already wrote that down. And our p hat, we've already written that down too, 90 over 150. And 1 minus p hat, that's got to be 60 over 150, because if you didn't say yes, you said no. And obviously, in some sense, the 150s cancel out and you get 90 and you get 60, and both of these are trivially bigger than 10. Normality check is met. You don't even need to write a sentence, but if you're feeling fancy, you can write, so normality of the sampling distribution can be assumed. Look how smart you sound just by adding that in there, using all those big words. We're moving in. We finished our checks. Now we actually have to construct and interpret. So to actually do the construction, what you want to do, you have 3 options, and you're just going to do all 3 of them, so you make sure you get those points. You're going to be naming it. You're going to give the formula. You're going to plug the numbers in. You're going to use the calculator. Let's do it. What is this called? This one is called the one sample I can't speak one sample Z confidence interval. I'm using CI. You're allowed to use CI in the test. One sample Z confidence interval for a population proportion. So you name it. Then, after you name it, you use the formula that we already know about, our p hat plus or minus z star multiplied by our square root of p hat times 1 minus p hat divided by the square root of n. And then after that, you plug all the numbers in that we have been working with. So our p hat is going to be our 90 over 150 plus or minus. We need to find our z star. If you weren't paying attention earlier, just want a quick recap of finding z star. I'll do it on the calculator for you, especially since it is actually exactly the same number as the one we did earlier. But just in case you forgot, we are hitting second, vars, inverse norm. The area is always 1 minus the confidence percentage, so I need to change that 95 to a 90. And we're going to get that 1.645 we were dealing with before. But I'm going to use the 1.6448 or 1.6449 is what I like to use. So 1.6449 multiplied by our big, huge square roots. 90 over 150, by the way, this is 0.6. I'm just going to write 0.6 here because it's too difficult to write that whole fraction out. 1 minus p hat is going to be 0.4. And then now you're dividing it by our sample size, which is 150. Then, after you've written all that out, then we're just going to cheat and use the calculator to be 100% certain that we've plugged all the numbers in. So, just like we were doing earlier, we are going to be hitting stat, tests. We're going to go scroll down to that letter A, the 1 proportion Z interval. Our X in this situation was 90, 150, same confidence level, 0.90, calculate it, and we end up with 0.53421, comma, 0.66579. You can skip a tiny bit ahead if you want, but I'm going to double check and prove to everyone this is exactly the same thing as if we had typed all that in ourselves, but just so we don't waste time normally. So if I were to go ahead and type all this in, if I did 90 plus 150, or no, divided by 150, whoops, and then I added, what is this going to be? I added 1.6449 times, and look at this, we got a big, huge square root with the crazy looking fraction of 0.6 times 0.4 divided by 150, and I type all that in, I get my 0.65579. Notice I get exactly the same number. And if I went ahead and changed that plus into a minus by scrolling a whole bunch, you had to get that 0.5342, the same exact number if we had just not used the calculator or not use the quick buttons and typed it all in ourselves. So, and again, on the actual AP test, if you had any of these things, you would get the point for the naming and the calculation. So that's the main thing, is you just want to write all of it down so you have it. But if you miss one of them, that's okay, because you don't need every single one of them to get the point on the actual AP test. Let's continue on. We're gonna go to we've constructed it. Now we have to interpret. The interpreting part is going to be the same for every single problem. We need to make sure that we've memorized the sentence structure. What we're going to say is, we are, is it 90%? 90%. We are 90% confident that the true population proportion of students at this large university. What are they doing? They're like exercising or something. Who don't get enough physical activity. We are 90% confident the true population proportion of students at this large university who do not get enough physical activity is between, and then you state the two numbers one more time. 0.5342, 0.66579. If you were asked on the AP test as like a part B to answer a question like, is it reasonable to believe that the majority of students don't get enough exercise? And you would say yes, because they're all, the entire confidence interval is above 50%. Or if they said, is it reasonable to believe that more than 60% do? Well, no, because 60% is on the inside of the interval, so we could, that is actually completely reasonable to be a little bit above or below it. But this is all we want to say. Please be careful. Do not use anything about the word chance or probability, because it immediately turns your grade into a quote-unquote I on that AP test. let's move on. We're going to go ahead and do our part B now. So we did all of part A. So obviously I didn't give even close to enough room for part A there. But I can at least do part B right here because this one is exactly the same as the question that we did earlier with our sample size margin of error stuff. So just to write it down one more time, we want our margin of error to be less than this 2.5%. So our margin of error has to be less than or equal to, and what our margin of error formula is the z star multiplied by our square root of p hat times 1 minus p hat divided by n. And from there, we want this to be 0.025 because that's how you write 2.5%. Has to be less than or equal to. We already found z star earlier. That was 1.6449. And then our p hat here is, it tells us use the sample proportion to estimate. So we don't use 0.5 like we normally do. We use 0.4 and 0.6. And it doesn't matter that those are flip-flopped. It actually should have been the other way around, but it literally doesn't matter. It's the same number when you multiply this commutative property, solving for n. So I'm going to start off by dividing both sides. We have 0.025 divided by 1.6449, just like last time. I know the next step I'm going to have to square everything anyways, so if I just square it now, then I don't have to look at that ugly square root anymore. So I have 0.4 times 0.6 divided by n. After that, I'm going to flip over both sides of the equation. Running out of room for moving this. All right, flipping over both sides of the equation here, and we're going to get 1.6449 divided by 0.025. We're squaring that bad boy. When you flip over both sides of the equation, the direction of the inequality switches. Has to be greater than or equal to, and we're going to have n on the top, and instead of putting 0.4 and 0.6 on the bottom, I know I'm going to multiply it over here, so I'm going to have a 0.4 times a 0.6, and you got to throw all those into the calculator there. And if you throw all that stuff into the calculator, interestingly enough, you actually get a different answer than the answer key, because the answer key uses 1.645, which is the number in the back of the book, or on those tables, but I don't use the tables, and I recommend students not use the tables since you can lead to rounding error, and you don't want to make rounding errors when you're doing stuff this important. So, and 1038.9, but we always round up, so 1038.9 greater than or equal n. So our answer we're actually going to say is 1039. You would round up, even if that was a 0.1, you'd still round up. You always round up because n has to be bigger than that number. So 1039, done. We're not talking about this question anymore. We only got one more problem to do. I am pumped to be finished. Let's do it. We're All Nuts Inc. sells bags of cashews that are advertised as holding 15 ounces of nuts. The quality control manager at the manufacturing plant is responsible for ensuring the true weight of bags is at least 15 ounces. Twice a week, he takes a random sample of 16 bags from one day's production, about 10,000 bags, and weighs the nuts in each bag. One day, he finds that the mean weight is 14.6 ounces with a standard deviation of 0.6 ounces. Below is a dot plot of the sample. So, letter A, describe the distribution. This is a review problem from earlier in the year, but we're going to tackle it right now. Letter A, describe distribution. When you describe a distribution, you always talk about the center. You talk about the spread. And you talk about the shape. You always talk about the center, the spread, and the shape. The center can be either the mean or the median, or visually where the center is. They tell you in the problem that the mean weight is 14.6. So the center is the mean. I'm just going to, I'm too lazy right now. The mean weight of nuts is 14.6. For the spread, the standard deviation of weight of nuts is 0.6. And the shape, this one over here, there's not really a shape at all. You know, I would just say, let's say roughly symmetric. How about that? Roughly symmetric roughly symmetric, no outliers, no obvious skewness, and we could even put the peak at, what is that, 14.7. Beautiful. All right, so center, spread, and shape, we talked about all three of them. We're done. Letter B, construct and interpret 99% confidence interval with a mean weighted cashews in one bag. So what are we doing? We're going to be doing our checks immediately. So our checks right away. Can we even do this? So our checks right here, random. And it says random sample was stated in the problem. Says so right here. So random sample stated in the problem. And then after you check for randomness, the next thing you gotta do is your 10% or your independence condition. To check that independence condition, all we have to say is 16 is much less than 10,000. And you could even do something like that. 16 is much less than 10% of 10,000. You actually don't even need to show any math, but if you want to say 16 is less than 1,000, that's fine. I don't care. I'm done writing this. Normality. So we doesn't say anywhere that the distribution is normal, so you can't do that. N is not bigger than 30. N is 16. So what we actually have to do in this one is we have to talk about if the dot plot or similar has any strong skewness or outliers. But we've already said earlier that no, there's no skewness and no outliers. So our normality is a dot plot shows no obvious skewness or outliers. And I'm going to do the same thing I did last time. I'm going to be fancy with it and end it. So normality of the sampling distribution can be assumed. So normality of the sampling distribution can be assumed. Boom. We did it. We checked all of them. Every single thing is done. By the way, on the actual AP test, if they don't give you a dot plot, you have to draw one. You got to like draw one off to the side. And if you don't draw one of those, they will not give you the check credit for the drawing. You actually have to draw the dot plot or box plot or histogram or normal probability plot checking the straight line. Doesn't matter to me. We're going on to the next thing. What is this thing called? This is called a one sample T confidence interval for population mean. And it is found by doing x bar plus or minus t star times our standard deviation divided by the square root of n. And filling in our formula here, what is x bar? It told us in the question that our mean weight was 14.6. To find T star, this is the first time we've actually had to find T star on a problem. So I'm going to go ahead and go over to the side, finding T star on a calculator. Finding T star on your calculator. All you're going to be doing is seconds vars inverse T. I didn't say it earlier, but you always use T for our means. I'm not going to go into it for this video, but that's how you always do it. The inverse T. Our area formula is exactly the same. Our area is going to be 1 minus the confidence percentage divided by 2. Don't forget, confidence percentage means you will need to actually divide by 100 to get the decimal version of it. And then your degrees of freedom, no matter what, is going to be n minus 1 for these problems. I'm, again, not going into what that means or why we're doing it, but we're just going to believe it and we're going to accept it for now that the degrees of freedom is n-1. If you'd like another video for that, I can do it later, but I'm sure there's some other YouTuber who's made beautiful videos about degrees of freedom. All right, over here, 14.6 plus or minus. We are now using our calculator to do this. So we're going to hit second vars, inverse t, area 1 minus our confidence percentage. It says 99 in the question, divided by 2, degrees of freedom, 16 minus 1. You can actually just write in 16 minus 1. Calculator even accepts that. Look at this. It can't think about it. It's thinking about 2.9467. So in this case, we have 2.9467. Look at that beauty. There we have it. And then we're multiplying by our standard deviation, which we were told in the question was 0.6 divided by the square root of 16. I don't know why I wrote that part in red. That part should have been in blue. Whatever. All right. We're going to go ahead and now, just like before, we're going to be hitting our buttons to figure out where the t interval is. So we're going to hit stat, tests. Now we're going to the t interval, which is number 8. Should write that down too. What is that? Stat, test, t interval. And that's number 8. Okay, anyways, stat t interval number 8. And you have 2 options here, data or statistics. This is the statistics one. We don't have a list of data that we're drawing from. You could do that in the actual test. We're not going to do that tomorrow. 2.949467 was not our mean. Our mean was 14.6. Our standard deviation was 0.6. Our n in the question was 16. And our confidence level is 99. And again, the calculator is going to spit out this number, 14.158. Comma 15.042. And just like I did before, I'd like to prove that instead of doing any of that, you could have just typed these numbers into the calculator if you felt like it, to have one less thing to memorize. 14.6 plus 2.9467 multiplied by 0.6 divided by the square root of 16. And I got 15.042. That's the same exact number as this one. And if I go up here and I change this plus sign into a minus sign, I get the 14.157995, which is the same as this 14.158. Beautiful. Anyways, we have done it. We've constructed it. But we still need to do the interpretation part. So the interpretation part is going to be, we are 99% confident that the true population mean weight of bags o' nuts is between 14.158, 15.042 ounces. Oof. All right. I'm done. Letter C's, I crossed it off because it's not part of the test. It's not part of this test anyways. It'll be part of a later test. Peace out, guys. Have a great rest of your day, and good luck on the test.